Welcome. Let's take a look at an introduction to the notion of the limit of a function of two variables. So the idea is that as points in the xy plane, so arbitrary points in the xy plane, approach a fixed point, we'll call that AB, then the limit of the function f of x and y is some real number L. If the limit from all paths approaching the point AB exist and are equal to L. So let's assume that this is the point AB in the xy plane, and we're going to consider all paths as x and y approach that point in the xy plane. Now, notice that this surface here is nice and smooth, so we're going to assume for the moment that this is the limit L. Let's take a look at these paths. So let's start with a path from the x-axis directly to the point AB. So on my surface here, that path would look something like that, and as the points in the xy plane get closer and closer to AB, these y values, or z values, these output values get closer and closer to this L. I could also consider a path coming direct perpendicular from the the y-axis, looking something like that as x and y get closer and closer to the point AB. And so these points on this path would produce output values that would appear on this surface looking something like this. And so these output values are getting closer and closer to L. And for this type of surface that is continuous, it has no discontinuities, no holes, no gaps. It wouldn't necessarily matter which path I could take. I could come at an angle like this, in which case the output values for those x coordinate and y coordinates would produce something looking like this on my surface. So when we talk about the limit as points x and y approach AB, what we're saying is that the output values for the function need to approach this common value L along any possible path. Now, what's nice is if we write this in limit notation, we'd write this something like the limit as the point xy approaches the point AB of the function f of x and y equals L. And then if this function f of x and y is continuous at the point AB, we can say that the limit as the points xy approach the point AB, that f of x and y is equal to f of AB. And this is only true if f of x and y is continuous at AB. Now, similar to what was the case in single variable calculus, when the function for which the limit is being taken is a continuous function, there's a lot of really nice properties. For example, the limit as xy approaches AB of a constant is a constant. The limit as xy approaches AB of a sum of continuous functions, we can simply evaluate both of those continuous functions and keep either the sum or the difference. So you might want to pause for just a minute here and make note of these various limit laws. so that you can use them in the future. Couple of things to notice though, places we have to be a little bit careful. When we're talking about the limit of a quotient, we have to make sure that the denominator, that limit, is not 0. If we're talking about the limit of a radical, it's going to be important what the index is, whether that's a cube root or a square root. And for this to produce a positive value, then we will need that f of a and b is positive itself. Let's look at a quick example. We want to find the limit as x and y approach the point 1, 1 of the function 4x plus 2y divided by the quantity x plus y. So the first thing we notice is that the denominator here is x plus y, and we can't have the limit of this denominator be 0 as xy approaches 1, 1. Now, fortunately, as xy is approaching 1, 1, both of those are positive values. So as those x and y values get closer to 1, 1, this sum will remain a positive number. So this should be fairly straightforward. We can simply substitute y for 1 for y, and x we'll substitute 1 as well. So we get 4 times 1 plus 2 times 1 all over 1 plus 1. So my numerator simplifies to 6, and my denominator simplifies to 2. Simplifying that fraction there, we get 3. So the limit of this function as x and y approach 1, 1 is 3. And this means that as the x and y values get closer and closer to the point 1, 1, the output values for this function get closer and closer to the value of 3. Let's look at a second example. In this case, we're looking at the limit as the point xy approaches the point 1, 2 along any path. And we're considering the function with xy minus 2x squared in the numerator and y minus 2x in the denominator. Now, recall that when we deal with a function and a limit of that function, what we're asking is how does this function behave, not at the point 1, 2, but as we get close to the point 1, 2 along any path. So keep in mind, this is not about the behavior of the function at a specific point. It's about the behavior of the function as we get close to the point 1, 2. So let's go ahead and take a look. Well, as we get close to the point 1, 2, notice that our denominator is going to have some issues. As we get close to the point 1, 2, my y value is approaching 2, so this y is approaching 2 minus 2 times x. Well, the x is approaching 1. So this denominator is approaching something that looks like 2 minus 2 times 1. So it's getting closer and closer to 0. So the limit of this denominator is 0. And if I do a similar analysis in my numerator, the limit of this numerator is 0 as well. So in single variable calculus, we learned a strategy to help us deal with cases like this. And that was to look to see if there were any common factors. And as I look at this numerator, I can see that it has a common factor of x. So let's go ahead and factor that x value out and see what we're left with. So we have the limit as xy approaches 1, 2. We're factoring an x out. That leaves us with y minus 2x, all divided by y minus 2x. Now, After factoring out that common factor in the numerator of x, I see that I have a common factor in my numerator and denominator of 1. Now again, let me remind you that we're not concerned what happens at the point 1, 2. We're only considering values of x and y along a path that are close to 1, 2. So this ratio of y minus 2x over y minus 2x that we've divided out is not really 0 over 0. It's a small number divided by that same small number. And so when we have two finite numbers and we divide it by itself, that becomes a 1. So we can divide these out because we're not really considering that x and y are actually equal to 1, 2. So having done that, we have the limit as x and y approach the point 1, 2, and all we're left with is x. Well, if we're along any path and the points along that path are approaching the coordinate pair 1, 2, then this function x is simply going to approach the value of 1. So what this is saying is not that this function is equal to 1 at 1, 2, but what it is saying is if I choose a path that leads to 1, 2, and I consider all of the points along that path, and the limit as I evaluate this function at those points, what's going to happen is the outputs or the values produced by this function are simply going to get closer and closer and closer to 1. I hope you find this helpful.